Air travel changed fundamentally in the past decade, and you probably did not even notice. Connecting flights are disappearing, ticket prices are dropping, and direct routes are everywhere. So let us talk about the pioneer aircraft that made it all possible. If you were not paying attention, you may not have noticed the revolution happening in the airline industry. The days of attempting to build bigger and bigger airliners are gone. The 850-passenger double-decker A380, the 660-passenger humped Boeing 747, these behemoths are simply being outcompeted by a new generation of planes. Many mourn the slow demise of these iconic aircraft. But you are benefiting from this change directly. The entire nature of air travel has changed to benefit you and your needs. Your local airport has more direct flights to distant lands than ever before. The price of those tickets is cheaper than ever. Connecting flights are becoming rarer as this new breed of plane takes over. The plane at the forefront of this revolution is the Boeing 787 Dreamliner, a $30 billion bet on the future of the airline industry. Boeing sat at the poker table and pushed all their chips forward, an all-in bet on a radical new future. And it paid off spectacularly. The 787 revolutionized not only how the airline industry operates, but how future planes will be designed and built. This is the breakdown of the 787 materials. By weight, 55% of the 787 is made from composite materials like carbon fiber reinforced plastics. This makes it the first commercial airliner made primarily with this new age material. The 787 is rivaled only by the Airbus A350 XWB, introduced 4 years after the 787 in 2015. So why are composite materials so desirable for the airline industry? And how has the 787 made the most of their advantages? Composite materials are made up of 2 or more materials. Take carbon reinforced plastics. They are composed of extremely strong carbon fibers bound together by plastic resin. Carbon fiber consists of thousands of tiny, thin fibers of carbon. It is incredibly strong in tension, up to 5 times stronger than steel and 1/5 of its weight. But these tiny fibers cannot create a solid part by themselves. Carbon fiber beside a human hair shows the carbon fiber is actually smaller. Just like human hair, carbon fibers can bend and flex and separate very easily. We need to bind them together with plastic resin to form solid material. Otherwise, they just form a strong but flexible fabric. That flexibility as fabric is exactly what makes composites so useful when creating the precise and elegant curves of a plane. With the right tooling and designers, composite components can be made into almost any shape imaginable. In the past, a disadvantage of making large aircraft components from composites was the time taken to manually lay up parts. Layers of carbon fiber and plastic resin had to be carefully constructed. It required skilled technicians and was inherently difficult to scale to the production quantities Boeing needed. To get around this, Boeing uses automated tape laying to produce massive aircraft sections. The 787 fuselage is created by wrapping carbon fiber tape impregnated with plastic resin around a rotating mold of the fuselage. This machine precisely controls the overlaps of the tape and the orientation of the fibers. This ensures we are getting the most out of the carbon tensile strength to resist internal pressure loads and longitudinal bending loads the fuselage will experience. One problem with this manufacturing method is that the part needs to be placed inside an oven to cure the resin. This hardens the plastic and creates a solid composite structure. Ovens the size of a wide-body jet airliner fuselage are not exactly common. This is often the limiting factor on parts made this way. It requires massive upfront investment to build a customized oven large enough to fit the part. But the benefits are well worth it. The first and most obvious is the strength carbon fiber provides. Previous generation airliners are typically pressurized to an equivalent of 8,000 feet. That is the same height as Mount Olympus in Washington state. High enough that the lower pressure reduces your oxygen intake. Your stomach will bloat as the air inside is higher pressure than outside. This is uncomfortable and exacerbates the effects of jet lag. But thanks to the 787's stronger fuselage, it can increase its internal air pressure to an equivalent of 6,000 feet, 25% lower in altitude and about 7.3% higher in pressure. That may not sound like a lot, but it goes a long way in making the journey more comfortable. My favorite benefit of the stronger fuselage is the absolutely massive windows. The 787 window compared to windows of equivalent aluminum airliners is absolutely massive. In aircraft made primarily from aluminum, having holes this large in metal panels would result in the buildup of stress at window boundaries. As stress contours deviate around the window, this stress does not exceed material strength. But over repeated pressure cycles, tiny imperfections in the metal can grow into larger cracks and eventually fail. Holes this large in an aluminum airliner would severely shorten the plane flying career before it needed fixing or disposal. But it is not a problem for the 787, thanks to composite relative immunity to fatigue. The carbon fiber construction provides plenty of benefits for airline operators too, because the fuselage is just one massive part. Boeing was able to eliminate all joints and all fasteners needed to join them together. Sections that used to be made up of 1,500 aluminum sheets riveted together using 40,000 to 50,000 fasteners are now just one massive carbon fiber section. Carbon fiber's strength to weight ratio already makes the fuselage lighter, but eliminating joints and fasteners makes it even lighter. The reduced weight reduces fuel burn significantly. This fuselage is also incredibly aerodynamic because it does not have thousands of little bumps and ridges all over it from those joints and rivets. These surface imperfections make the plane's surface rough and cause it to disturb more airflow, increasing parasitic drag. Composite materials help reduce drag in other ways too. One of my favorite things about the 787 is its elegant wings. The main structural member of a wing is the wing spar. Its primary role is to resist the upward bending force during flight. It is essentially just an I-beam, a shape optimized to resist bending loads. The wing spars of the 787 are constructed from carbon fiber composites, while the ribs, the structural members connecting the two spars that support the wing skin, are machined out of solid aluminum plates. The structure the rear and forward wing spars form with ribs running between is called the wing box. It forms the main load-bearing structure of the wing, while also being a literal box for fuel to sit inside. The carbon fiber composite spar provides the wing fantastic strength. Strength is quantified by the force required to completely fracture a material. But carbon fiber composites have another important quality that makes them perfect for aircraft wings: their maximum elastic strain. There are two types of deformation: elastic and plastic deformation. Elastic means the material will snap back into its original shape after the load is removed like an elastic band. Plastic means it will permanently deform and will not return to its original shape once the load is removed, something we do not want to happen. This is permanent damage. Carbon fiber composites can deform further before they strike this plastic deformation zone at about 1.9%, while aircraft aluminum begins permanently deforming at less than 1%. That means we can bend carbon composites nearly twice as much before causing permanent damage. This allows Boeing to create thinner, more elegant, and more efficient wings. The wings can flex dramatically during flight without suffering permanent damage. This flexibility actually improves aerodynamic efficiency by allowing the wing to adapt to different flight conditions. Beyond the airframe, the 787 engines represent another massive leap forward. The Gen X engines fitted to many 787s incorporate breakthrough technology that revolutionized fuel efficiency. The engines achieve a pressure ratio of 58:1. This is record-breaking. Higher pressure ratios directly translate to better thermal efficiency and lower fuel consumption. But achieving these high pressure ratios created a major problem. Higher compression leads to higher temperatures. Higher temperatures result in increased emissions of potent greenhouse gases like nitrogen oxides. Nitrogen oxide formation rates rise exponentially with flame temperature. To facilitate increased pressure ratios while hitting climate change goals, this problem had to be addressed. They did it through ingenious fuel injection technology. The compressor feeds its high-pressure air into 22 fuel mixing nozzles located in a ring around the compressor exit. Their job is fairly simple: mix the fuel into the air and ignite it. A simple job that started development in 1995 with both General Electric and NASA. The art of crafting the perfect fuel injection nozzle is incredibly complex, a delicate yet violent process, like an orchestra whose crescendo is a fiery explosion. With the advent of 3D printed manufacturing, GE has been able to create a fuel injector with a complex internal labyrinth of air channels that traditional tooling simply could not cut. The fuel injector they developed is called the Twin Annular Pre-Swirl Injector, or TAPS. It avoids dangerous nitrous oxide emissions by carefully controlling the air-fuel mixture ratios to control flame temperatures. The TAPS fuel injector uses a large amount of air in the pre-mixing phase to ensure thorough mixing and a lean air-fuel mixture. This may seem like a simple device, but it took generations of design iterations with computer simulations, gradually bringing engineers closer to their target. None of their designs would have been possible without current generation metallic 3D printing that could manufacture the complex parts with materials capable of resisting the enormous heat within the combustor. 26 years of development paid off with 60% nitrous oxide emission reductions, a fuel injector compatible with the record-breaking 58:1 pressure ratio used in the Gen X. All of these factors combined to allow the Gen X engines of the Dreamliner to reduce fuel consumption by 15% over previous generation engines. That is an astronomical leap. And on top of all that, the engine is 60% quieter than similar sized planes, in part thanks to the engine's most distinctive feature, the sawtooth pattern on the fan casing and the engine exhaust. These features are called engine chevrons. They are not just futuristic cosmetic design, but functional parts of the engine that significantly reduce engine noise. Because turbofan engines force air out of their bypass chambers and turbines at speeds much higher than ambient airspeed, the air interacts with the free stream air, causing mixing. This mixing causes uncontrolled vortices, which generate excessive noise for both passengers and the community on the ground. The chevrons aim to control the vortices shed from the engine nozzle by creating smaller vortices at each of the teeth of the chevron. This allows the hot, fast air being expelled from the engine to mix with the ambient air more gently. This is said to reduce jet blast noise by as much as 30%. It allowed Boeing to use substantially less sound insulation in the fuselage walls, which helped reduce aircraft weight. The 787 truly does live up to its name. It provides a passenger experience almost incomparable to other commercial aircraft, with advances in noise reduction, fuel efficiency, and passenger comfort. The 787 could be the most advanced piece of engineering in commercial aviation. And it is a plane many of us will have the opportunity to fly in and marvel at the decades of engineering advancements that made it possible.